So lipids pack about 2 times the caloric content of carbohydrates, right? So where was the caloric content of carbohydrates stored? Does anyone remember? It was in the glycosidic bonds, right? So these are stored in the glycosidic bonds. Here, in a lot of lipids, we have things like triglyceride and triglycerols, and those are going to be stored also in different bonds throughout the molecules, depending if it's a simple lipid or a complex lipid, but also in the ester bonds a lot of times. So we looked a little bit at lipids. What was the lab we did where we looked at the alcohol, basically a 3-hydroxyl alcohol that, I think it was the esterification lab, where we actually made soap where you had a lipid made there. And so in that type of bond is where we're going to have energy stored. So they pack about 9 kilograms per gram oxidized, right? So when we're oxidizing, we're doing what? Other way around, right? We're going to be, if we're oxidizing, we're going to be gaining carbon-hydrogen bonds and losing hydrogen. And then right, that's where the name oxidizing comes from. And if we're reducing, then we're gaining hydrogen, gaining electrons, right? So that means when we're oxidized, if we have something like an ester bond, and we'll go through more the structure of lipids in a little bit, then we're going to be gaining carbon oxygens, or if we have, so for example, when we did I won't do the ester bond, I'll do the, what was it, if we had an alcohol, for example, then we get oxidized by adding a carbon-hydrogen bond and losing adding a carbon-oxygen bond and losing a carbon-hydrogen bond. So when we oxidize the fats, then we burn energy in that process. And so carbohydrates are used for immediate energy, whereas lipids are used for energy or the storage of energy, right? So, that's why the body naturally holds on to the fat stores, because we're going to use that energy later. We're saving that energy for later in the form of lipids and fats and oils, and then carbohydrates are usually used for immediate energy, which is why if you're a runner or something, usually, or an athlete, usually the night before a big anaerobic exercise, you do a big carbo load, right? You eat a lot of bread or something like that. Sugars tend to be even more immediate energy, whereas the amylose and amylopectin that you have in bread, takes a little bit longer to break down. And so lipids are also going to be the main component for, does anyone have an idea for the cells in our body? What are lipids used for? The membrane. So these are going to be main component for the membrane of the cells in our body. So these specifically are going to be phospholipids a lot of the time, and these phospholipids have specific properties that allows them to be good membrane creating molecules. And also fats and oils and stuff are important because there are a lot of vitamins that are fat, and then I have a blank there, that we would be deficient if we didn't have fats in our body. And so lipids, we'll learn, they kind of have dual properties depending on the part of the molecule that you're looking at. And so a lot of vitamins are actually what we'd say are fat soluble. And if they're fat soluble, that means if they're in a solution that has fat and water, they're going to be going to which side of that, right? So if we have something fat, which is nonpolar, and something polar, like water, the fat-soluble vitamins will go to which side of this kind of divide? The fat-soluble, right, fats, we'll learn are going to be, like I said, they have dual properties to it, but they'll be able to solubilize in the nonpolar, right? So fat-soluble is going to move to the nonpolar side of this divide here. And so when we talked about some enzymes, I think it might have been Sarah that came up at the end of last lecture. Lipids are going to have a polar side and a nonpolar side a lot of the times, and that's what allows them to make good membranes. But there are also proteins, for example, that are designed to have part of their structure be nonpolar and the other part polar. And these proteins are good for membrane proteins because the nonpolar part sticks inside of the cellular membrane, the nonpolar part, and then the polar part can stay outside and present itself to the solvent. So again, these ideas of intermolecular forces interacting with the structure of these different types of molecules kind of doesn't really go away. Okay. Any questions on any of this, or people still writing here? I'll give you guys a second to write. And so next we're going to talk about the classification of lipids. Lipids kind of have a lot of different classifications. There's two ways that we'll really classify them. A lot of times lipids are classified based off their physical property because they're some of the earlier biological molecules that people were looking at, because you see it a lot, for example, in cooking, right? You see fats and oils there all the time. Okay, and so lipids, so instead of being classified by the functional group, so they're not going to be classified by the functional group, right? Where carbohydrates, we looked at those acetal groups, and they were either aldehydes or ketones, right? The functional groups help classify them. Or proteins, if we were to classify proteins in terms of their functional group, what would you say they were? Can you have an idea? Right, so functional groups. We have carbs, which were aldehydes, ketones, and they were polyhydroxyl of these, right? That's what carbohydrates were. What about proteins? How would we classify proteins? Did anyone have any idea? Yeah, they're amino acids, right? And amino acids, so the functional group for a protein, they're made up of amino acids. And what are the functional groups that are on amino acids? Yep. Carboxylic acid. Carboxylic acid, and it isn't an alcohol side for an amino acid. Right, so acid, carboxylic acid, amino. It'd be an amide bond, right? So amide is kind of the general classification for peptides and polypeptides, right? It was the amide, right? Because the amides formed the functional group that formed what special bond in proteins? The peptide bond, right? This was the peptide bond. And so is the carboxylic acid, and then we have our C terminus and our N terminus, which was the amine, right? So that was the amine. So we don't have a carboxylic acid, which is usually an alcohol, or an ester would be an alcohol and a carboxylic acid, and an amide is a amine and a carboxylic acid, right? Both of those go through hydrolysis or condensation reactions that involve water. One, you're just protonating an OH group, and the other one you're protonating an oxygen, and the other one you're protonating a amine group. Right, so both of those biological molecules were classified by these functional groups, right? These are the characteristic functional groups of these molecules. Lipids are going to be a little bit more complicated because we, as names suggest, we'll have simple lipids and complex lipids, so it makes it intuitive that they're going to be a little bit more complicated than that. And they're not necessarily going to be classified by their function group, but rather their physical property, which is usually going to be solubility, right? And then we'll talk about another classification that's kind of more modern classification of lipids on the next slide. And so the solubility, are these going to be soluble in aqueous solutions or not, right? So are they soluble in aqueous solutions or not? And so this is, not just a simple yes or no question. It'll be determined based off of the individual lipid. And so we can break these down into steroids, fatty acids, and fatty acids I'm not going to have you guys memorize all the different classifications of all these lipids. We're probably going to focus on, we'll talk about steroids, fatty acids, triglycerides, waxes, phosphoglycerides, and we'll probably maybe do a little bit of sphingolipids and glycolipids. So we're not going to have to memorize all this, but we'll be able to talk about the different properties of this, and then based off of the properties, determine if they're going to be, either soluble or insoluble in aqueous solution. And when we say aqueous solution, that means what? Yep, so this is in H2O, right? So what types of things are usually soluble in water? I think I hear some people say alcohols, right? So OHs. What else could be soluble in water? If you were to put it under one umbrella term, what would you say? What kind of molecules? What was it? Yeah, it'd be polar, right? So OHs or polar molecules in general. Like, so polar molecules would be soluble in aqueous solutions. And again, this is going to go back to the idea within lipids that we kind of have two parts of the molecule. One part that might be polar and one part that might be non-polar. Okay. The other way that we can classify lipids is basically, can the lipid undergo saponification, which will be one of the reactions that we see for lipids as well. And what was saponification again? It would be the opposite of a condensation reaction. Yep, it would be a hydrolysis reaction. And hydrolysis is generally classified as what kind of reaction? Right, if we start from one larger molecule and go to smaller molecules. Decomposition, right? So this hydrolysis, which is a decomposition reaction. And then what's special about, so why don't we just call it hydrolysis? Why do we call it saponification? Does anyone remember why? So water, whenever we hydrolyze water, that's why we say hydrolysis, right? Because water is always going to be a product, whether we hydrolyze it or saponificate the molecule. So this one we start from an ester and we break it down into two components. Claire?
This was the one that we did with soap.
Yep, this is the one that we did with soap, right? Does anyone remember the specific conditions that were involved in making the soap? It has to do with the conditions of the reaction. So hydrolysis on its own is usually acid catalyzed, and saponification was base catalyzed, right? So this is a hydrolysis reaction that is base catalyzed. So this reaction can happen if we have acid present or base present. And if we have a base present, right, the only difference is when we hydrolyze an ester, instead of creating a carboxylic acid, what do we create if we have a base present? Right, if we take an ester, I'll come back to this slide in a second. If you guys want to finish writing this line, I'll let you guys finish writing this line, but on the next slide, we'll go over real quick what hydrolysis looked like. Bless you. Hydrolysis looked like for a generic ester. Okay. So for a generic ester, that one might be me. It would be R1. What's the functional group of an ester look like? Where's the O go? Here? Is that what you guys are saying? So go O up first, right? There's a single bond there. Double bond, right? So it's a double bond to an O. And then what else? And then another O right here. And then this is the functional group of an ester. So I'll make this the second, right? And so whenever we hydrolyze something, we can do it in acid reactions in the presence of water is usually present in this reaction. And are we going to be hydrating or dehydrating these molecules? So this one we're actually going to be hydrating, right? Because when we break up a ester, we go into a carboxylic acid and an alcohol, right? Which means that we need to add an OH group and we need to add a water group, right? So how this breaks up is we get something like this, R2, right? This is how these molecules broke up when we hydrolyzed this reaction. And the water molecule, one proton went to the O in the OH on the carboxylic acid, and the other OH went to the alcohol side of the carboxylic acid. Right, so this would just be regular hydrolysis. And then we also have, where it really doesn't change anything, we can have sodium hydroxide and water. And this would be saponification. Is just base catalyzed hydrolysis of this reaction. So this would then go to R, O plus R2. Actually, I'm going to just draw it in the correct orientation. OH, R2. And the only thing that really changes here is when we did this, these two molecules tended to change. So what's wrong about what I wrote down here? Potentially. If we have a lot of base in solution, what is the pH of that solution going to be, high or low? It'll be high, right? So because we have base, this makes the pH high. And if the pH is high, what form of the carboxylic acid do we prefer usually? Right? We think about the protonation of this carboxylic acid side, right? And let's just say the pKa, we'll say it's a relatively not that acidic, is around 5. We have base in the solution, right? Which means that the pH is going to be about 13, right? Or up to 13 potentially. So what does that mean for the protonation state of the carboxylic acid? It should be deprotonated.
Is that where you get the carboxylate ion?
Yeah, that's how we get the carboxylate ion, right? So this O minus O should look like that. Right, and if you remember when we made soap, the soap was basically just a fatty acid salt, right? That's how we classified it. It was just fatty acid salt because we did this, and then this coordinated with maybe a sodium ion or something. And this is what made soap if R1 is equal to fatty acid, which we'll talk about in a second. Right, so this hydrolysis and saponification, these are two of the reactions that we're going to end up seeing with lipids. And so here I just wrote in an arbitrary ester, but you'll be given some examples where you actually have specific lipids and fatty acids to predict the products for hydrolysis.
What does FA mean?
Fatty acid.
Are you recording? Are you recording?
Yeah. All the lectures are recorded, so
Great.
however useful some of you may find it.
So
So
it's only if the ionization, is that the right way to say that?
yeah, it is. It's an ionization.
Okay, so is that only when the solution is super basic?
So it doesn't have to be only when it's super basic. That's a good rule of thumb. The more basic the solution is. Generally, the pKa's, right, when we're talking about amino acids, the pKa's for the C-terminus, because it's part of the peptide bond, are really low. So those ones are pKa of around like 2, is what I remember looking at those. So the pH can be neutral, and it'll still be in its deprotonated form, which is why the C-terminus of amino acids is usually deprotonated, which for oxygen means that it'll be negatively charged, right? If you have a fatty acid, the pKa's for those tend to be a little bit higher. So if it's neutral, it probably still will be deprotonated most of the time, right? Because we want these polar sides of the lipids and the fatty acids. So it'll probably still be deprotonated, but it probably doesn't take as high of a pH for that to happen. And remember, we're always, if we want to see if it's protonated or not, we're just looking at the pKa value for that carboxylic acid. And again, we'll go into more detail on fatty acids and what this actually means. But these types of hydrolysis reactions and the saponification was a specific base catalyzed hydrolysis reaction. And so this is another way that we can catalyze or classify the different lipids that we have. And so we can have, and I don't like these words, these can be broken up into non-saponifiable, it is a word, believe it or not, non-saponifiable lipids and saponifiable lipids. And we'll talk about a little bit of the non-saponifiable lipids like steroids, but the other ones, not as much. And then these are either simple lipids or complex lipids. So these get broken down into two categories, which are either waxes or triglycerides. And then complex lipids, like phosphoglycerides or sphingolipids, those are going to be basically lipids that'll have other functional groups on them. The simple lipids are going to be comprised of basically carboxylic acid and a saturated or unsaturated non-polar tail. And we'll probably get through fatty acids today for simple lipids, and the next time we'll probably get through all of waxes and then some of the complex lipids, and then maybe talk a little bit about the non-saponifiable lipids. So this is another way of classifying lipids, and this is probably how people generally think of it more now. And that's because this hydrolysis reaction is important for using fats and oils as energy. One more time. So you're talking about this one right here, right?
Yeah, for the red, are we adding the Na plus or are we
the Na plus is just if you have that in solution. So that was just when we made the example of when we made soap. So this is something separate to these hydrolysis reactions.
Okay.
So this is like usually when you add when you have basic conditions, you do the saponification, you add sodium hydroxide. So you dissociate the sodium from hydroxide, which then catalyzes the reaction. It creates a deprotonated version. The deprotonated version then coordinates with the sodium atom to create a fatty acid salt.
Okay, so if we were writing it, would we still do the like?
You would do the deprotonated version. Right? I just drew it in a couple steps, but this would be technically the more correct version of what you would do. So you'd have a carboxylate ion rather than a carboxylic acid.
Okay.
Right. And so it makes sense. If you have really acidic conditions, you add H3O plus that lowers the pH below the pKa of the carboxylic acid side, and then that'll keep it protonated when you do that.
Gotcha. Thank you.
Okay. Oops. Oh, this is the wrong. All right. Okay, so simple versus complex lipids. Simple lipids are only composed of alcohols and carboxylic acids. And so one of the common one we thought, so you saw that triglycerols fell into the category of simple lipid, and that is basically a glycerol, which is a trihydroxy alcohol. And so that would be something like CH2OH, CHOH, CH2OH. And then the other component is the fatty acid, which is the carboxylic acid acid side of this molecule. So if we had carboxylic acid, and then a long nonpolar chain or something. So this would be the carboxylic acid, and this could be the alcohol. And so this would, if we were to combine these into a single simple lipid, then we would take 3 of those to combine with 1 glycerol molecule, and that was what we did when we made soap. Right, so this would be the condensation or the esterification reaction that would happen if you take glycerol and then 3 different fatty acids, and you combine them to make a simple lipid that's just comprised of an alcohol. Right, so this is the alcohol and then the carboxylic acid. And then complex lipids are going to have these and then potentially other components. So we may have something that has a glycerol molecule that combines with a fatty acid, but maybe the fatty acid 3 times OH has some other amine group on it or something like that, right? That's what makes it a complex lipid. Or for example, we think about a phospholipid, right? The phospholipid has a phosphate side of the lipid and then a long long nonpolar chain attached to it. And so that phosphate side of the lipid is no longer an alcohol, it'd be a phosphoglycerol or something like that, right? So that changes what this whole side of the molecule could potentially look like. So I'm writing them in their individual parts. They haven't fully formed to form the triglycerol or the triglyceride or the complex lipid yet. This is basically before we've condensed these molecules into a simpler complex lipid. Okay.
So the difference is that a complex lipid has an amine?
It doesn't necessarily have to have an amine. This is just an example of what it could have, right? So
This has something.
example, it has something extra. So this can be anything extra, right? So it could have maybe multiple hydroxyl groups along the side chain or something like that as well. Okay. So first we'll talk about fatty acids. So these are going to be carboxylic acids that are the structural components for fats, oils, and lipids, right? So again, the simple lipid had both an alcohol and a fatty acid side to it. They usually have an even number of carbon atoms and are unbranched. So that's why usually you see lipids drawn like this. They're not branched structures, right? So this means that if we have the carboxylic acid side of the molecule, it will look something like this and not something like this, where we have a lot of branching of the nonpolar chain, right? So for example, carbohydrates, you could have branched polymers because when we saw the glucose or fructose, that was the difference between amylose and amylopectin, was that was a branched polysaccharide versus a linear polysaccharide. right? Because those ring structures could go off in a bunch of different directions, or they form a nice linear chain. So this one on the right is what you would not see for fatty acids. And so these are usually classified by the number of double bonds. And so we've seen this before when we talked about alkanes and alkenes in when we first started talking about organic chemistry. And so if we have a saturated fatty acid, what do you think that means? This would be no double bonds, right? So this would be no double bonds and only CH bonds, right? So these are simple lipids, so we're not going to have CH and CC bonds. Right, so there's not going to be any other odd functional groups to throw us off. And then unsaturated fatty acids will be what? These will have double bonds. And within unsaturated fatty acid, usually it's classified two ways, right? If we have a single double bond versus multiple double bonds. And so how do you think those will be classified? What about multiple double bonds? If we have multiple of something, what's usually the prefix we use whenever we have that? Yep, it'll be a poly unsaturated fatty acid. And then if it's only a single one, what do you guys think it'll be? A monounsaturated. And what you'll find is that just based off of the degree of saturation or unsaturation of the fatty acid, that'll change the physical properties by quite a bit. And it's something that you see every day, or potentially every day, depending on how much you cook. Right, so it's, unsaturated fatty acid is going to have double bonds in there. And if you think about a long chain, and we add a double bond, we can think about how that affects the structure of the fatty acid. Right, and so let's give you guys a second to finish writing if you're still writing. Right now, maybe think about how does a double bond affect the structure of when we looked at alkanes versus alkenes, right? In a double bond, the carbon is hybridized how? sp3 has how many bonding partners? 4, right? And if we have a double bond, right, it'll have at maximum 1, 2, 3 bonding partners, right? So it'd be sp2. In sp2, what is the shape of the sp2 hybridized? Trigonal planar, right? And so that means that you can't have rotation around this bond. So if you have a fatty acid, and all of a sudden you either have a cis or trans configuration, that'll affect how this chain actually looks, right? Because we're restricting this bond to a single plane. All right, is anyone still writing this? We'll talk about that. The next slide we talk about the structure of the fatty acids. All right, so fatty acids have a blank side and another side. So what are the two sides to the fatty acids you guys think there's going to be? And then there's, nonpolar and a polar side, right? And what do you think is the nonpolar side of the fatty acid? So we won't just describe it as inside or outside yet, because actually you can have just a single fatty acid in solution, and depending on the ratio of what you have, this is a membrane bilayer, because there's 2 layers of fatty acids here to make the membrane. But you can also have a single layer or just single fatty acids. So on the nonpolar side, we'll describe that as the the long hydrocarbon chain, right? So this will be the long hydrocarbon chain, right? That'll be the nonpolar side. Let me write that a little neater. And that'll usually look something like, we'll have CH2, N, and then CH3, right? The edge will be CH3 if there's not a double bond there, and then you have a lot of, if it's unsaturated or saturated, then you just have a bunch of CH2s repeating. And then the polar side is going to be what for the fatty acid? It'll be small. It'll be a smaller relative to this side, right? And so the fatty acid, as the name suggests, one side will be, it'll be polar, and then what specific functional group is going to be at that side usually? So it'll be a water-soluble side, right? And what functional group, though, right? It's a fatty acid. It'll be a carboxylic acid side. So this is going to be the polar side, which is the COOH, the carboxylic acid. Or if it's in higher pH, the carboxylate ion on that side. And so at low pH or high pH, the structure of the fatty acid is different because in both of these cases we're looking at the protonation state of this oxygen. So this is the same thing as we looked at the protonation state of the different amino acids, the C terminus and the N terminus. At low pH, when the pH is low, we favor which form of the fatty acid, right? And this is true for any functional group, right? At low pH, so if the pH is low, it's going to be if the pH is lower than the pKa, right? So this really what this is saying is pH is lower than pKa, we favor protonated. And then if the pH is greater than the pKa, we favor the deprotonated. I'll do that in different colors. So this will be OH, this will be O minus. And if we think about this, this will be the more polar version of the fatty acid, right? We don't have a proton to neutralize the full negative charge there. So this is going to be the more polar version, which is generally why we see this version in at neutral pH, right? So biology has evolved to basically have this more polar version at neutral pH. And so this part of the structure is the polarity, the non-polarity within the molecule of a single fatty acid. This just deals with the carboxylic acid side and then the nonpolar tail. The next thing is basically the degree of the saturation or the degree of unsaturation, however you want to phrase it. That affects the shape and also the physical properties of the fatty acid. Right, so if we have trans versus cis double bonds, the number of carbon atoms in the nonpolar chain can also affect the physical property. So this, if we're thinking about, how does chain length affect London dispersion forces, that'll affect intermolecular forces, which then affect the physical properties of the material, or of the fatty acid. All right, if they're cis or trans double bonds, then also the number of double bonds as well. The structure of fatty acids in both dealing with the polar, non-polar properties, and then also the degree of saturation, and that's going to affect intermolecular forces as well. And one way we can look at this is just the melting point of fatty acids. And so if we have a saturated fatty acid, the molecule will look something like this, and we have an arbitrary chain like this, right? So this forms a nice little flexible chain, and it's relatively straight, right? So we think about this, this is relatively straight molecule. If we have an unsaturated fatty acid, we could have something that has double bonds that are all in the trans configuration, like that, which will probably have similar properties to what the saturated fatty acid, may be slightly different. Or we can have things in the cis configuration. Whenever we have something in the cis configuration, see, I'm going to draw it the other way, it'll affect the three-dimensional shape of the molecule. It'll be something like that. It'll create a kind of kink or bend in the molecule. And if something is going to be in the physical state, do you think the molecules are going to be closer, or sorry, not the physical state, in the physical state of a solid, do you think the molecules are going to be closer together or farther apart? Closer together, right? They'll be close together when they're closer together, they'll be in the solid state. When they're farther apart, they'll either be in liquid or the gas state. And so because, if I was to circle this part of the molecule, it's going to look something like this. These are all going to be little alkyl groups, something like this. This is be like an electron density map, is what the fatty acids look like if you looked at their potential, how things can get close to each other. These would all probably be able to align in a nice, neat, packed orientation like that, right? They're all straight molecules. They're all pointing in the same direction. They'll be okay orienting themselves this way and being able to line up, right? If we have something like this, and again, this is our polar side of the molecule, and we kind of have these alkyl groups and then a bend in the molecule. So what I'm doing right now is I'm going from the carbon skeleton just to give it kind of like what a three-dimensional shape would look like. If these were to try and orient themselves, they would have maybe a bend going in one direction, bend going in another direction like that. This saturation has introduced a bend or a kink in the fatty acid's nonpolar tail. And that makes it, do you think, harder or easier to pack close to each other? It'll make it harder, right? So this is going to be harder for it to pack close to each other. And how do you think that affects the melting point or the boiling point of these fatty acids? It'll be a lower melting point, right? So the lower the temperature is, it'll be in the liquid form because it's harder for them to pack closer together, right? So this is going to have a lower melting point, and this will have a higher melting point. And the reasoning for that is because these molecules can pack neatly because they are straight chains. And then the opposite is true for the unsaturated fatty acids. If they have a trans configuration, right, in the kink in the acid, that really won't affect the structure very much because they'll still stay linear molecules. And obviously when I say linear, I'm talking about kind of the macroscopic shape, not obviously, but I'm talking about the macroscopic shape of the molecule, right? Because overall, this entire group forms a line, right? This is like a solid line that this whole molecule forms. Whereas here, there's a bend in the line. That's how I'm getting these lines that I've drawn right here. Individually, each atom obviously has a complex tetrahedral or sp2 geometry, so it's a little more complicated than that. But if we zoom out a little bit, all these molecules compact neatly in linear orientation with respect to each other. And so that affects the melting point that way. What about the length of the side chain? How do you think that affects the melting point? Right, so if we think about, if we have two, let's say, unsaturated fatty acids, or saturated fatty acids, sorry. If we have these two molecules, which one do you think will have a lower melting point? So you think the bottom one will have a lower melting point, and what's the justification for that?
Because it's more, or it's like.
So if we're thinking about polarity, that would be a good argument, except it would probably have the opposite effect, right? If it's more polar, if it actually has a dipole moment in the fatty acid, then you have dipole-dipole interactions now, which would be a stronger intermolecular force. But intermolecular forces are the way to think about this. And so if it did actually make the molecule polar, then that would be a stronger, because it has a permanent dipole, which is going to have a stronger force than normally the type of interactions that they would have with each other. Here, I'm not really trying to focus on the degree of polarity in the molecule, but what's changing between these two fatty acids?
Amount of carbons.
Yep, the amount of carbons in the nonpolar side chain, right? So the amount of carbons in the non-polar side chain and how would the amount of carbons affect the intermolecular forces, right? So if we have something that's non-polar, how does the number of carbon atoms affect the intermolecular forces there? What type of intermolecular forces are present, I should say? Right, the London dispersion forces. And the more electrons you have, the stronger or weaker London dispersion forces are. The stronger, right? So as the molecular weight goes up, London dispersion forces go up. So the more carbon atoms you have in the non-polar side chain, the stronger the London dispersion forces of the molecule, right? So this then implies that the top one will have a higher melting point, and then the bottom will be a lower melting point. So when we're looking at fatty acids, we could look at the degree of polarity of the molecule, and that might have a small effect. But really, once we start getting anything above 5 carbons total, right, the molecule isn't really thought of as polar anymore, because the nonpolar part of the molecule dominates or determines a lot of the intermolecular forces that are present there. And so this can be slightly affected by the degree of saturation too, because if we have a polyunsaturated fatty acid, then you've removed a lot of hydrogens potentially from the molecule, which can affect the London dispersion forces. But that's a much smaller effect than just adding 1 carbon, right? Because adding 1 carbon is the same thing as adding 12 hydrogens. You'd have to have a lot of hydrogens removed. Okay. Any questions on that? That's a good point. The longer the chain, the higher the melting point is going to be, right? Because the London dispersion forces are stronger, so they can feel stronger attraction to each other. Mm-hmm. Anyone still writing? All right, so if we look at these 4 fatty acids, predict what state of matter you would expect to see at room temperature. Right, and so you guys have seen different fatty acids at room temperature. If we look at things like oils versus butter, coconut oil, those are all going to be fatty acids or triglycerides. So based off of these structures, predict if it would be solid or liquid at room temperature. And I hope with the reference, I'll say that this one is solid at room temperature. That is going to be solid. What do you guys think the first compound is going to be? It would be solid liquid. Yeah, so you put liquid for this one. And what's the justification for that? Yep, it's poly unsaturated with cis configurated double bonds. Cis configuration double bonds. Right, that makes it harder for these molecules to line up and stack on each other, and so it is more likely to be found as a liquid. Right, we can't maximize the interaction between the chains because of the shape, and so they are going to have weaker intermolecular forces. What about the longer unsaturated or the longer saturated fatty acid? Solid or liquid? Solid, right? Because if this one right here is already defined as solid, this one is going to have stronger or weaker intermolecular forces compared to that. Stronger, right, because it's a longer chain, so it's going to have stronger intermolecular forces. So that one's also going to be solid. If that one's solid, the shorter chain, then the longer chain is definitely going to be solid. And what about the last one? What do you guys think? Liquid. This will probably also be liquid because it's unsaturated. And so this was solid because, so if I put A, B, C, D, because if B is solid, yeah, that one's also polyunsaturated, but one of them you have a trans configuration for the double bond, and the other one you have a cis configuration for the double bond, which is why it doesn't bend as much. It doesn't introduce as much of a kink to the curve because one of them is trans, and trans will keep the linear structure. And the intermolecular forces of C are greater than B, then C is solid. All right, so that's how we predict the physical state of each of these fatty acids. What's up? Yep, liquid is going to have a lower melting point. Right, if the melting point is higher, that means you have to reach a higher temperature before it starts to solidify. Right, so this might be a melting point of 30 degrees Celsius, and then anything that has a lower melting point than that will be liquid at room temperature, right? If its melting point is 20 degrees Celsius, that means at room temperature it'll be a liquid. So that's probably like what coconut oil is, right? Because coconut oil, if it's cold outside, it kind of solidifies, but if it's moderate, temperature, it probably stays mostly liquid, and then if it gets really warm, it stays completely liquid, right? So if you ever keep coconut oil in your pantry, you'll see that. So that melting point is probably exactly around room temperature. Okay. So then these fatty acids can also form what are called micelles. So it depends on the type of solution, right? So if we have a carboxylic acid, we'll do COO minus, will be the carboxylate, and then a non-polar side chain there. What kind of solution? So, and basically what a micelle is if I was to draw it, is we would create, it's a single layer of fatty acids like this. Right, where the color coordination there is the same as what I drew in the upper right-hand corner. So what kind of solution do you think that this would be soluble in? In nonpolar or polar? Right, so which part is exposed to the surroundings? The polar part, right? The carboxylic acid or the carboxylate side. So the polar side is exposed to the surroundings. So what kind of solution do you think this structure will be created in? In a polar solution or a nonpolar solution? It'll be a polar solution. So this will be an aqueous solution. Solutions, bless you. Fatty acids can make micelles. And what these micelles are is we have the orientation or the kind of separation of the nonpolar parts and the polar parts of the molecule to then shield the nonpolar parts from the outside polar solvent. So in the surroundings, we might have water like this. And so that's what you guys are going to be doing today in lab, is you're going to be making micelles and observing what happens to the micelles when you do some different things to the reaction.
So
Andrea?
The blue circles are the polar part, right?
The blue circles are the polar part, yeah. So it's the same coordination as what I have over here. So that's the polar part. Andrea, did you have a question?
It brought up to mind makeup remover,
Mhm.
micelle water.
Yeah, so from my understanding is because oleic acid and things like that, which are supposed to be good for your skin and whatnot, when you put it in aqueous solution, it forms these little micelles, and when you rub it on your skin, you break up the micelles. And then you expose your skin to oleic acid. I think that's the acid that's in makeup remover. Is that it? Does anyone know? I probably don't know anything about this. I've never worn makeup, but yes, that's why people are like, I don't know what's in it. Well, how much of everything you put in your body do you really know what's in it, right? But yeah, so oleic acid, I believe, is a fatty acid. And then when you put it in aqueous solution, it forms these micelle structures. And so these micelle structures can be pretty important for biological processes, for movement and transfers of fats. So in the lumen of the intestine, you can have these fatty acids and monoglycerides that then kind of solubilize into water to form these micelles. And once they're in their micellar form, they can then be absorbed through cellular walls or semi-permeable membranes within the body, where they can then further be broken down and used for energy and energy storage, right? So this is important for the transport of fatty acids, fats, and oils. The formation of these micelles. And so also, people are looking into using micelles as a form of delivery for certain drugs. So if you can engineer the surface of these micelles to have certain groups, maybe that target cells that take in more glucose, for example. So a lot of times people say cancer cells pull in a lot more glucose. So if you modify the fatty acid to have a group on there that, is attracted to glucose, or proteins on the surface of the cell that are exhibited when the cell has extra glucose inside of it, you can then design these micelles to have something on the inside that has probably what kind of properties. Right, if you have a micelle, I'm going to draw the structure again, like this. And let's say you want to deliver something to a specific area in the body. What type of molecule would you be able to put in the center of this micelle? Just based off of physical property.
A nonpolar?
Yeah, you'd put a non-polar molecule, or maybe a therapeutic fatty acid or something like that. Maybe, oleic acid or something if it's for your skin. So you put a non-polar molecule in the center of the micelle, and then the polar side still allows it to float through solution, and maybe there's another group on the polar part that then allows it to target specific cells, right? So targeting is a big question in modern research for medicine. If you can, that's what's bad about chemotherapy, is that it kind of kills everything, but if you can get it to at least go to the right place, then it'll reduce the damage that it does, right? So it's important for transport processes just in your own body, and then it's also something that you can use to your advantage if you're trying to design something to move something to a specific location within the body. And so that's what you're going to be looking at today in lab, is the formation of these micelles. And so, and I've drawn it in 2D here, but really these micelles are three-dimensional structures, right? They actually form a sphere where they're all pointing inward. You just can't really draw that. They really look kind of more, see if I can do my best to draw it. So if this was like a sphere of all the non-polar sides going into the corner of like we're kind of cutting out a corner of the actual micelle itself. Okay, any questions on micelles or micelle formation?
When you see that someone can make something within the body, can you give me an example of what you mean?
When someone can make something within the body?
Yeah, I think you said something.
Like when you deliver something within the body? Yeah, so if you have a non-polar therapeutic or something, like you need to deliver it to a certain part of the body, and you know that, I don't know, I can't think of any specific examples, but the liver uptakes a certain vitamin more than other cells in the body. You can design the micelle so that the body might think that it looks like that vitamin, right? And so if the surface of the micelle is coated with stuff that the cells think is something else, they'll pull it into the cell, and maybe inside the cell you actually have something completely different. Maybe chemotherapy or some other drug that can then interact with whatever molecules in the cell you want. And so, it's kind of like you can deliver aspirin directly to the receptors for aspirin. It's kind of the idea with that. You can put aspirin inside of a micelle, and instead of having to wait for it to naturally flow through your bloodstream, you can maybe ingest some micelles that then directly deliver it to the area of interest that you're looking for. Aspirin you don't really need to worry about because it doesn't matter if it gets other parts, but for chemotherapy, for example, it's bad if it gets other parts. It'll kill other healthy cells as well.
It's like a delivery, like a catalyst.
Yeah, it is kind of like a personalized delivery system for the drug. And, it's a hard thing to do because, when you're in the macroscopic world, you have tools and stuff to kind of put things together. But in the microscopic world, everything is determined by intermolecular forces. So how do you trick your body into feeling like this thing is something that it's not?
It's like painkiller.
In sense, so painkiller is going to usually dull a receptor. This is, and it directly, in a way it is, right? Because painkiller, you have something that binds to something that really isn't supposed to be binding to it, and so then that nullifies that receptor in a way. So this is like you're kind of tricking the body into taking in something that it doesn't necessarily want to based off of its interactions with its environment. And so people do this with micelles, but also, with other types of structures as well. They build protein cages, they try and use viruses, all these other things to deliver these drugs like this. It's actually a pretty big field. Like if you could detect or develop a system that could specifically target any cell in the body, you would probably win, like I said, a Nobel Prize for that, because it's hard to teach your body to just take this and not something else that looks very similar to each other. Okay, so we'll stop there today. Next time we'll continue talking about fats and oils, and then we'll get into more complex lipids and then some of the non-saponifiable lipids.